In today's video, we'll be talking about something called impedance. Something quite remarkable happens when we're dealing with AC voltages and currents. When our inputs are sinusoidal, the resistors, inductors, and capacitors that we've been using throughout the entire course actually all follow a form of Ohm's law. This means that AC circuit analysis actually becomes a little bit easier than DC, since everything can be thought of as a resistor-like component. What we're going to do today is derive expressions for the impedances of a resistor and an inductor, and then I'll tell you what it is for a capacitor. Then, in the subsequent videos, we'll be using these complex impedances to do analysis of the circuit. Let's begin with resistors. If our voltage is given as follows, now I'm giving you a VM, a magnitude, not RMS. It turns out it's not going to matter much. As long as I specify which one I'm using, we can be consistent and we'll still know the answer is correct. So the way we derive an impedance is by looking at how does the voltage and the current relate in the element. We don't need anything special for AC. We can use all of the expressions we already know. For a resistor, we know that V equals IR. What we're going to do now is we're going to try to derive an expression for the current. Well, that would mean that the current is V over R, or Vm over R cosine omega t plus phi. As a phasor, this voltage was given as Vm angle phi. The current as a phasor is given as Im angle phi, where Im is Vm over R. So, a couple of remarkable things that we need to remember. First of all, we can just use Ohm's law for resistors. It still works no matter what your input is. Second, the phase does not change in a resistor. We're going to see in an inductor and a capacitor that you do in fact have a phase change. Let's now go on to inductors. Once again, we're going to assume that V is Vm cosine of omega t plus phi. Now, we know that through an inductor, and remember, all I'm doing is just using the equations that we already know. I of t is 1 over the inductance, integral from 0 to t, Vm cosine omega t plus phi dt. If I carry out this integration, I get negative Vm over L sine of omega t plus phi. And remember, I'm a lot more interested in dealing with cosines. Again, that's just a convention. It just makes things consistent. So I have sine omega t plus phi is actually given as the cosine of omega t plus phi minus 90. Which means that my current waveform is given as I of t equals to Im, the magnitude, which is here, multiplied by, or not multiplied by, but just generally discussing the angle, minus 90 degrees. Now I've just realized I've missed one thing, which is that the magnitude actually contains the omega. Remember, when we do the integral, we have to essentially undo the derivative, and that omega would have been there. So this is what Im is. Im is negative Vm over L, the inductance, times omega, and for the most part, this is not really relevant, the negative. The reason being that as things start to alternate, positive and negative, it's hard to determine where you started. We'll keep it in there for now, but it's not really relevant. Now we're not done. We can see that this phi minus 90 here implies that we're actually dividing two phasors. In fact, it almost looks as though we can rewrite this as follows. The current through the inductor is Vm angle phi over omega L angle 90. Or, perhaps a different way of saying this, is Vm is omega L angle 90 degrees IL. Now, if I'm going to do that, this looks a lot like Ohm's law. V equals to IR. Because it's a little bit confusing to use the letter R for both a resistance and something that's not quite a resistor, we tend to call this Z. Z is the symbol we use for impedance. And the term basically, again, is used to describe the fact that it's not a resistor, but it is still impeding the flow of current. So whereas in DC, resistors resisted current, in AC, we still have this resistive sort of property going on. We just call it an impedance, and that implies whenever we use the word impedance that we're dealing with an AC voltage. Now we can do a little bit more with this. Let's take a look. That impedance was given as W, or omega, sorry, times the inductance, angle 90 degrees. Remember, phasors are just complex numbers. So let's see what complex number this becomes. Well, I might call this ZL, the impedance of the inductor. And this is an impedance that is aligned with 90 degrees, the complex axis, which means as a vector, it's 0 omega L, or as a complex number, it's J omega L. And here I'm going to introduce another notation. J is the square root of -1, which we've typically called I in the past. Once again, we're trying to avoid confusion. I can be confused with current, and we don't want to do that. So we just use the next letter over, J. Sometimes you'll see things as I and sometimes as J. It's usually clear from context which one we mean. So, we've so far derived two impedances. ZR is equal to just the resistor value. ZL is J, or I if you prefer, omega L. And that's for an inductor. By a very similar derivation, we'll see that ZC, or the impedance of a capacitor, becomes 1 over J omega C. Or if you'd prefer, negative J over omega C. And what I did there was I just multiplied top and bottom by J. J times J is -1, so I have negative J on top and omega C. Both forms are useful. What does this mean? For capacitors and inductors, impedance depends on omega. This is something we do not see with resistors. With a resistor, I can pass any sine wave I want through that resistor and will still follow just basic Ohm's law. It will not be dependent on the frequency. For inductors and for capacitors, they are. I want to go through one very quick reason why this is relevant. Here is a circuit, and this is a voltage given sinusoidally. Here's an inductor. Let us say that V is equal to Vm cosine omega t. We're not going to worry about phase right now. It doesn't matter. And we're curious about what the magnitude Im is. Well, we can still use Ohm's law. V equals Zi. Everything so far will work fine. Z is j omega L, or omega L angle 90. I is what we're curious about. V, we know, is Vm angle 0. I haven't given you a phase. Let's now solve for I and see what we get.
Okay.
I, as a phasor, is going to be Vm angle 0 over omega L angle 90, or Vm over omega L angle negative 90 degrees. So, what does that tell us? A couple of things. The first one, as omega tends to infinity, as omega gets very large, I's magnitude, which is this quantity here, tends to 0. Which means that for very large frequencies, inductors essentially block the current from coming through. They act as open circuits. It's kind of neat. Number 2, I lags V in an inductor. And this concept of lagging or leading needs some diagrams to explain. If this is my current waveform, then to lag by 90 degrees means that essentially this point here is moved back. I beg your pardon, this is my voltage waveform. And then my current waveform, which I'll draw as a dotted line, might come down like this. What this means is that V and I are referred to as out of phase. In this case, by 90 degrees. Lagging. In a capacitor, you can do the same analysis, and you'll find that the current leads by 90 degrees. If you want to remember which one is which, you can use the acronym CIVIL. For capacitors, the current leads, because I comes first, the voltage. The voltage leads the current in an inductor. Or, as we've been saying with lagging, the current lags the voltage in an inductor. This is useful, and will become more useful in subsequent videos when we talk about what a load could be interpreted as. For now, just remember that it's possible for the current and the voltage to be out of phase with each other. That's going to have some interesting properties when we deal with power.